Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. Last time I was talking about the sixth equation, which is an identity. So let's look at that, how it comes up. And since we have seen so much in spherical coordinates, I'll continue with that. Okay. So let's say I have my axis of rotation and my element here. I'll draw it a little big. Okay. So what are the resultants? Basically this is the question. What are the resultants that are involved in alpha 3 rotation? That's the question we are asking. Okay. So those will be n phi theta incremented n phi theta, n theta phi and incremented n theta phi. The increments are smaller order terms or higher order terms, so they will not participate. Okay. Additionally, there are moments, we will account for that, twisting moments. The diagram gets clustered, so I am first dealing with just these. Okay. So phi is my first coordinate, theta is my second coordinate. And let me say that this rotation I will consider as positive. Okay. So if we look at the moments caused by these two forces, okay, so let us see. I get n phi theta, okay, make it a force r sine phi d theta, okay, and multiply by the momentum, this momentum, okay, that is r d phi by 2, okay. Then next is the moment due to this, so let me include the increment n phi theta into the incremented length, which is r sine of phi plus d phi d theta, again into r d phi by 2. Okay. So this is also in that direction. Then the reverse moment due to these two. What is that? Minus n, there is no, I am ignoring the increment here and the length is the same. So I get minus n theta phi made into a force r d phi, okay, and the mean length between the two, which is r sine phi plus d phi by 2 d theta. Okay. So this is the moment arm and this is the force. Okay. So now if we do all the additions, we get n phi theta r square sine phi by 2 d theta d phi plus n phi theta r square d theta d phi by 2 sine phi cos phi d, hold on, plus cos phi d phi minus n theta phi r square d phi d theta into sine phi plus cos phi into d phi by 2. Okay. So if we drop the smaller terms, we have is equal to n phi theta r square sine phi d theta d phi, okay, and minus n theta phi r square sine phi d theta d phi. Okay, these are different, mind you. This is n theta phi, this is n phi theta. So that's one set of terms, the moments due to force resultants. Okay. Now moments, there are twisting moments which will do the same now. Okay. So if I draw my element once again, this is element with some thickness. Now by conventions, okay, that is now my theta direction and this is now my alpha direction. So this moment, this twisting moment is m phi theta, positive side, and this twisting moment is m phi theta on the back side. Okay, I am ignoring the increments now. I am ignoring increments. Okay. Then this moment on this twisting moment is m theta phi, and twisting moment in this face is also m theta phi. Okay. So now let us look at m phi theta. Okay. So we have m phi theta along this line. Okay. So if I represent a moment, this moment using a diode, okay, using a right hand rule and the diode is a double arrow heads. Okay. So if you use the right hand rule, this is going inward into the plane of the paper. The right hand rule goes into the paper. Okay, the forefinger moves into the paper. Okay, so if I represent these twisting moments using diodes now, okay, and I draw this in a different orientation, that is this line, and this is a diode that is going inside. Okay, that's the, you use the right hand screw rule, it will move or it will point inward. Okay, similarly the one on the left points also inward. Okay, and this angle is too big. That angle, let us say, is d phi by 2. d phi by 2. Okay, and what component causes the rotation about alpha 3? This is my alpha 3, that's alpha 3, right? So the vertical component causes rotation. Okay, so we said this rotation is positive. Okay, we will stick with that. So m phi theta will give you that rotation, and I am looking for the vertical component. Okay, so if I say that this is d phi by 2, that is d phi by 2. Okay, so this is d phi by 2, so I am looking at the sine component of it. So I have m phi theta. Okay, then let me make it a moment, actually multiply by r sine phi d theta. Okay, and I am ignoring the increment of this also now because it is a second order term. So m phi theta into r sine phi d theta, that is the full moment. Okay, and the component vertical. So here also the vertical component, and both are in the same direction. Okay, so multiply by d phi by 2 into 2 from both sides. Okay, so that gives me m phi theta r sine phi d theta d phi. Okay, now for the other side. Okay, for the other side. The other side is the moments m theta phi, m theta phi. Okay, so if I now draw the view looking like this, I get let me keep it a bit shorter. Okay, so now if I use the right hand rule, this is going down, it's going down. Similarly, this is also going down. Okay, so this is going out like this. This is on the right hand side here. This is going down here. This is on the left hand side, m theta phi and m theta phi. Okay, so I need again the vertical components here, vertical components, but they will now cause a moment in the opposite direction, negative direction. Okay. Now, what is the angle I want? If you recall, this angle is sine phi d theta by 2 from earlier derivations, because this is at the midpoint with this as d theta. Okay. To be more specific, this is r sine phi plus d phi by 2 d theta. Okay, that's the same length as this at the midpoint. Okay, now because of that, the angle turns out to be sine phi d theta by 2. So this angle is that angle. Okay, then this angle is that angle. Okay, so now, and this angle is that angle. So I need the sine of this angle. So what I will get is m theta phi, okay, into r d phi, which makes it a full moment, into sine phi d theta by 2, that is for each moment, multiplied by 2, and a minus because this is causing rotation in the opposite direction. So this is equal to minus m theta phi r sine phi d phi d theta. Okay. So now please watch. If we add all these up, quite interestingly, it looks like this: r square sine phi d theta d phi n phi theta minus n theta phi, okay, plus m phi theta by r minus m theta phi by r. Okay, that must be equal to 0. Okay, because again we are ignoring the rotational inertia of this differential element. Okay, now watch what happens. If we now bring about the definitions of force and moment resultants, okay, what do we get? We get n phi theta minus n theta phi plus m phi theta by r minus m theta phi by r. Okay, that is going to be equal to, now I bring in the definition of resultants. Okay, so here this is sigma phi theta into 1 plus alpha 3 by r2 d alpha 3 integrated over alpha 3 minus integral over alpha 3 sigma theta phi 1 plus alpha 3 by r1 d alpha 3, okay, plus integral alpha 3 sigma phi theta alpha 3 1 plus alpha 3 by r2 d alpha 3 by r, this is this term m phi theta, okay, minus integral alpha 3 sigma theta phi alpha 3 1 plus alpha 3 by r1 d alpha 3 by r. Okay. Now if I put this together, all terms together, I get integral alpha 3 sigma phi theta 1 plus alpha 3 by r2 1 plus alpha 3 by r, okay, minus sigma theta phi 1 plus alpha 3 by r1 1 plus alpha 3 by r d alpha 3. Okay. Now r1 is equal to r2 is equal to r, okay, the radius of the shell. Okay. I wrote it in this way because just to remind you of what the resultants, moment resultants are, okay, from the definition. But otherwise for the spherical shell this is what it is. Okay. So now if I look at this, I have, if I replace r2 by r, so I have sigma phi theta minus sigma theta phi 1 plus alpha 3 r 1 plus alpha 3 r. In the general case you will get r1 and r2, okay. For a general case you will get r1 and r2, but in this case it's both are r. So let me keep it that way. Now this is indeed equal to 0. Why? Because sigma phi theta is sigma theta phi. Okay. So the so called approximate dynamical equation is actually an identity. It's the sixth equation. Okay, and I've told you the reason why it doesn't appear in the Hamilton's principle. Okay. So that is one point I wanted to make. The other point I wanted to make is this. Now we have Hamilton's law, okay. Let's say for a just for the Euler-Bernoulli beam. Euler-Bernoulli beam. We end up finally with equations of this form: minus integral t1 to t2 integral 0 to L rho BH W double dot delta W minus integral T1 to T2 integral 0 through L E B H cube by 12 del 4 w del x4 delta w dx dt, and then the boundary terms plus integral t1 to t2 e b h cube by 12 w triple dash delta w 0 L dt minus integral t1 to t2 e b h cube by 12 w double dash delta w dash 0 through L dt is equal to 0. Okay, so if we combine the differential equation terms or Euler-Lagrange equation terms, we get the differential equation of the form t1 to t2 integral 0 through L e b h cube by 12 plus del 4 w del x4 plus rho b h w double dot, then delta w dx dt plus the boundary terms, the two boundary terms must be equal to 0. Okay. Now, how do we say that each of these terms must be 0? This term must be 0 independently, that must be 0 independently, this must be 0 independently. How do we say that? Okay, so that comes from the lemma of the calculus of variations. Principal lemma of the calculus of variations. I just wanted to mention that. And what does it say? If f of x is continuous, in AB, in some interval AB, and if integral a to b f of x and some h of x dx is 0 for every function h of x belonging to C0, okay, in AB, a continuous function such that at the end points HA is equal to HB is equal to 0. Here is the key. Then f of x is 0 for all x belonging to A comma B. Okay, so this takes the role of f of x, this takes the role of h of x. Okay, so the way to show that independently this term is 0 is, first of all you take variations delta w which are 0 at the boundary points and slope derivative which is 0 at the boundary points. You take such a variation. When you do that, this term is 0 and that term is 0, okay, and you are left with this term, you are left with this term, and then you apply this lemma. There are proofs of this lemma in various books, you can look it up, okay. Now you have a delta W just like h of x, which is 0 at the boundary points, okay, that is how we chose it, okay, and then this is a continuous function, okay. So the theorem or the lemma says that this coefficient term has to be 0, okay. In a very simple manner to prove that is, suppose it is not 0, okay, I am just giving a very quick version, okay. Suppose it is not 0, suppose it is varying between A and B, okay, or let us say it is positive somewhere, it is positive somewhere, okay, maybe 0 at other places. Then I will choose my delta W such that it is also positive in the same zone, okay, and it goes away to 0 towards other parts, okay. So then what happens is that the product of f of x, which is now positive, and the product of h of x or W delta W together, it is positive, okay, the integrand now is positive. So now if you integrate f of x and h of x, then you will get a non-zero value, it won't be 0. So similarly, if there is a region where f of x is negative, then I will choose my delta W or h of x to be negative there, okay, because I have the freedom to choose delta W, and then the f of x which is negative and delta W which is negative together will give you again a positive value, which if you integrate will not be 0, okay, and therefore f of x, if that has to be 0, f of x has to be 0 throughout, okay, and it is a continuous function, so it is not jumping wildly. So if it has a non-zero value at the border, it will have a non-zero value for a while, okay, before turning sign. So again I can use the same argument, I will choose a delta W or h of x, okay, because h of x is 0 at the border. So I will choose a value such that it is positive or of the same sign as my f of x. So that will result in a non-zero value of the integral, okay. So that is a sketchy proof of the lemma of calculus of variations, and that is how you show that the differential equation independently is 0, and then you get boundary terms. You get a boundary term which delta W, and then you get a plus or a minus boundary term with a delta W dash, okay. Now here the strategy is actually that we find first delta W and delta W dash such that they are 0 at the boundaries, so that the boundary terms are not there, okay. Then we prove that the differential equation by itself holds and goes to 0. Then once the differential equation term is not there, then we again look at the boundary terms, okay, and now we choose delta W such that it is 0 at the top and lower boundary, so that this boundary term is 0, okay. Then we are left with this boundary term. Now this boundary term by itself is 0, so that gives me the boundary conditions. Okay. So now this term, the partial differential equation is 0 by itself, this boundary term is 0, okay, by itself. Then once these two terms are removed, then I have this boundary term, which now by itself again must be 0, okay. And that is how we get the PDE and the boundary conditions, okay. So we have run out of time for now, so I will close the lecture here and we will continue from the next class. Thank you.